Welcome back to Tech Talk. Today, we're delving into the world of recommender systems. These algorithms are everywhere, from suggesting movies on Netflix to recommending products on Amazon. They're crucial in helping us navigate the vast sea of information online, but building effective recommender systems comes with its own set of challenges. To unpack all this, we've got two amazing guests. Is an expert in reinforcement learning and its applications in recommender systems. And Dr. Raim brings us a wealth of experience in the field of recommendation systems. Thanks for having me. It's great to be here. Recommender systems are indeed fascinating, but they're constantly evolving. One of the biggest challenges is capturing and modeling user preferences accurately. We need to understand what users like, how their tastes change over time, and how to predict what they might be interested in next. Absolutely. And the sheer volume of data in today's digital world makes this even more complex. You've got to sift through massive data sets, handle the cold start problem where you don't have enough user data, and deal with the constant noise of user behavior. So how does reinforcement learning come into play here? This is where Dr. Lisa Chim's expertise really shines. Right. The paper we're discussing today explores the use of reinforcement learning, RL, for building more powerful recommender systems. RL is a machine learning approach that focuses on how an agent can learn the best strategy for interacting with its environment to achieve a specific goal. Think of it like a robot learning to play a game, where it tries different moves, gets feedback in the form of rewards, and slowly learns the optimal way to win.
That's a great analogy. It really helps visualize how RL works. In the context of recommender systems, the agent is our recommendation algorithm. The environment is the user and all their data, and the goal is to make recommendations that maximize user satisfaction.
Exactly. And the key aspect is that the recommender system learns through interactions with the user. It's not just passively analyzing data, but actively making suggestions and adjusting its strategy based on how the user responds. Doctor, can you walk us through the methodology behind the paper? How do they model the recommendation process using RL?
Sure. The paper uses the Markov Decision Process (MDP) framework, which is a standard tool for modeling sequential decision-making problems in RL. Imagine a user browsing a movie streaming service. Each time the user interacts with the platform, the system is in a state, for example, the user's watch history, their current mood, or the time of day. The system then takes an action, suggesting a movie. This leads to a new state, based on the user's response, like watching the movie, adding it to their watch list, or skipping it. The goal is to learn a policy, a set of rules that tells the recommender system which actions to take in each state to maximize the long-term reward. And in this case, the reward is usually based on user engagement, like how much time they spend watching a movie or how many movies they watch.
So, the recommender system is constantly learning from the user's feedback and adjusting its recommendations to get the most positive response possible. That's pretty interesting. Now, you mentioned there are different types of RL algorithms. Can you explain those in more detail?
Absolutely. We have three main categories: value function approaches. These methods focus on learning a value function that assigns a numerical score to each state based on how desirable it is for the agent. The agent then chooses actions that lead to states with higher values. Think of it like a map where each location is assigned a value based on how close it is to the goal. The agent would always choose the path that leads to locations with higher values. Policy search methods. These methods directly optimize the policy, the set of rules that dictate the agent's actions, without relying on the value function. They use gradient-based techniques to find the best policy parameters. This is like training a machine learning model that learns to predict the optimal move in each situation. Actor-critic algorithms. These algorithms combine the best of both worlds. They have both an actor, a policy network that makes decisions, and a critic, a value function network that evaluates those decisions. They learn together, with the critic guiding the actor towards better decisions. It's like having a team where one member makes decisions and the other provides feedback to help them improve.
That's a very clear explanation. So the paper explores how each of these approaches can be applied to different recommendation scenarios. Can you walk us through those scenarios?
Sure. The paper focuses on four main scenarios. 1. Interactive recommendation. Think of a user browsing an online store. The recommender system is actively interacting with the user, suggesting products based on their past interactions and providing personalized recommendations. The goal is to learn a policy that maximizes the user's engagement and purchase probability. 2. Conversational recommendation. This is a more advanced scenario where the recommender system has a conversation with the user, asking questions to understand their needs and preferences before providing recommendations. This is like a personal shopper assisting you in finding the perfect outfit. RL can be used to learn the best dialogue strategies to guide the conversation towards optimal recommendations. 3. Sequential recommendation. This scenario deals with recommending items to users based on their past purchase or interaction history. For example, recommending movies based on what the user has watched previously, or recommending music based on their listening habits. RL is useful here for capturing long-term user preferences and recommending items that are likely to be enjoyed in the future. 4. Explainable recommendation. This is about providing not only good recommendations, but also explaining why those recommendations are made. For example, a system might recommend a movie because the user has enjoyed similar movies in the past, or because the movie has a similar theme to movies they've watched before. This is achieved through path reasoning over a knowledge graph, KG, a large database that contains information about entities and their relationships. RL can be used to learn the most effective reasoning paths within the KG to provide accurate and understandable explanations.
That's a really diverse set of scenarios. It's great to see how RL can be applied to all of them. And, Doctor, I'm sure our listeners are curious about the results. What did the paper find?
The results were quite promising. The paper demonstrated that RL-based recommendation methods consistently outperformed other approaches in all four scenarios. For example, in the interactive recommendation scenario, the RL models were able to learn a more effective strategy for suggesting products, leading to higher engagement and purchase rates. In conversational recommendation, the RL models were able to guide the conversation more effectively, leading to more personalized and satisfying recommendations. In sequential recommendation, the RL models were able to predict future user preferences more accurately, suggesting items that the user was likely to enjoy. And in explainable recommendation, the RL models were able to generate more accurate and informative explanations for their recommendations, making the system more transparent and trustworthy.
That's really impressive. I can see how this research has real-world implications. Dr. Field Expert, from your perspective, how do these findings translate into real-world scenarios? Can you give us some examples? Absolutely. Imagine a streaming service like Netflix. They can use RL to personalize recommendations based on a user's viewing history, their ratings, and even their interactions with the interface. RL can help them recommend movies the user is likely to enjoy, keeping them engaged and subscribed. Or think about Amazon's product recommendations. They could use RL to learn how to suggest complementary items based on a user's past purchases. This could lead to increased sales and a more satisfying customer experience. Even platforms like YouTube can benefit from RL. They could personalize recommendations based on videos the user has watched, liked, or disliked, helping them discover new content they might enjoy. It's fascinating to see how RL is being applied across so many different platforms. But we need to be mindful of the challenges too, right? It's not all sunshine and rainbows. Can you tell us about some of the challenges encountered in this research?
Of course, while RL holds great promise for recommender systems, there are some critical challenges. First, we have the issue of data biases. Recommender systems often rely on logged data, like user clicks and browsing history. But this data can be biased, reflecting only the items users have seen and chosen. This can lead to RL algorithms learning biased policies that favor popular items and ignore less popular but potentially interesting ones. Another challenge is reward function definition. Choosing the right reward function is crucial for guiding the RL agent towards the desired behavior. But defining a reward function that captures all aspects of user satisfaction can be difficult, and it can vary across different scenarios. We also face challenges in computational complexity. RL algorithms can be computationally expensive, especially when dealing with large datasets and complex environments. This can make it challenging to train and deploy these models in real-time scenarios.
Those are all critical issues, and I'm sure our listeners are wondering, what are the potential solutions to these challenges?
The paper explores a range of solutions. For example, to address data biases, they propose using techniques like off-policy correction and inverse propensity scoring. These techniques try to account for the biases present in the logged data and learn more robust policies. To tackle the reward function definition problem, they suggest using generative adversarial networks, GANs, to learn a reward function that is based on user behavior. And to address computational complexity, they explore techniques like task structuring, which involves breaking down the recommendation problem into smaller, more manageable subtasks. They also propose using hierarchical reinforcement learning, HRL, where the agent learns to make decisions at different levels of abstraction, reducing the overall computational burden.
That's promising. It sounds like there's a lot of exciting research being done to overcome these challenges. Doctor, from your experience, what are some other key challenges and opportunities in the field? What are the broader implications of this research? Well, the research definitely highlights the potential of RL for recommender systems, but there's still a lot of work to be done. One of the biggest challenges is evaluating these RL based systems. Traditional metrics, like accuracy, are not sufficient. We need to consider other factors like diversity, novelty, and explainability to truly capture the user experience. We also need to be more mindful of fairness and ethical considerations. Recommender systems should not perpetuate biases or create unfair outcomes for certain groups of users. And we need to make sure these systems are explainable so users understand why they're being recommended certain items. This will help build trust and transparency in AI. And finally, we need to address safety concerns. Recommender systems should be designed to prevent harmful or unethical recommendations. This is a critical area where more research is needed to ensure these systems are reliable and safe for all users. It's clear that this research is pushing the boundaries of recommender systems, and there's a lot of exciting work ahead. Doctor, what are your thoughts on the future of RL-based recommender systems?
I'm very optimistic about the future of RL-based recommender systems. This research shows that RL can effectively learn complex recommendation strategies, leading to more personalized and engaging user experiences. As we continue to address the challenges, I believe we'll see a significant impact on real-world applications. I think we'll see recommender systems that are more adaptive, more efficient, and more transparent. They'll be able to learn and adapt to user preferences in real time, provide more diverse and novel recommendations, and provide clear and understandable explanations for their decisions. This will lead to a more personalized and enjoyable online experience for everyone.
It sounds like a bright future for recommender systems. Doctor, any final thoughts on where this field is headed? I couldn't agree more. RL has the potential to revolutionize recommender systems. As we continue to refine these techniques and address the remaining challenges, we'll be able to build systems that are truly intelligent, adaptive, and beneficial for all users. It's an exciting time to be in this field. Thank you both for this fascinating discussion. It's clear that RL is playing a critical role in shaping the future of recommender systems. We'll be following this research closely and reporting on its progress. And for our listeners, be sure to check out the links to the paper and the researchers' work in our show notes. Until next time, stay curious.